kick off the Pioneers Reception 2024. Thank you guys for coming. I've got a lot of thank yous here. I want to thank Andres Bourbano for allowing us to change the format of what we usually do. You guys know that we usually meet off-site at a hotel in a ballroom somewhere, and what was hoping to do this year, and Andres was very gracious to allow us, is to have our Pioneers Reception be open to the entire SIGGRAPH community. So most of our, talks in the past, and we've had just amazing talks in the past, but they've only been accessible to the pioneers. So I wanted to be able to let people who are attendees of the conference itself come and hear our fascinating speakers. So thank you to Andres. Thank you to Deanna Dyer for all of her help. Oh my God, where would we be without Deanna? And thanks to the Freeman AV crew. For the first time, we're having the actual Freeman AV crew record the session. I'd like to get feedback from the group, so just send me emails when you can if you want to continue doing it this way, where it's more integrated into the conference itself. For the first time, we have leftover food. I've never seen leftover food at a Pioneers Reception, so that's just awesome. I also want to say thank you to the Pioneers Steering Committee. There's a number of people on the steering committee. We meet once a month by Zoom, the second Wednesday of every month. And if anybody would like to be involved in the planning for all these things, because I'm not the one who does all this planning, the steering committee does all the planning, and I have a lot of help from a lot of people. And if anyone who's a pioneer would like to be on the steering committee, just tell me, I'll add your name and you'll get the Zoom invite, or evite, and you'll be able to help us out. And I also want to thank the steering committee for asking me to be chair for 3 more years. So I'm going to be your chair till 2026. I do want to just quickly go over, what have we done in the past year? So anyone who was here last year for the 50th anniversary celebration, we compiled a reel of every pioneers who wanted to, old videos of your early research, and we put together a reel that's 4 hours long, and it was playing in the time tunnel room last year at the conference. That 4-hour video is available online. If you want to see any of the videos that we've done, just Google SIGGRAPH Pioneers, and it'll take you to our page, and there's a link for online contents. And that online contents link will show you lots of videos, all of the panels that we've done. And this year we did 2 amazing panels on artificial intelligence and how it relates to computer graphics. We had 4 amazing speakers. Last year, of course, Jim Foley and Andy Van Dam were our speakers. We also this year did an online schmooze fest, which was a name that was given to just our online chat, where there was no set agenda, but everybody could just interact with everybody else on Zoom. And we're going to do at least one of those, and the feedback was great from that. We have done interviews with a lot of the conference chairs, And so I've been editing those one by one. We have a number of those online posted. I wanted to make an announcement. Julian Gomez asked me to tell you guys that there's going to be a Birds of a Feather session on Wednesday, tomorrow at noon in room 706 to talk about the Center for Computer Graphics History. And I'm really excited to find out more about that. So one of the sad things that I do every year, I've been editing an in memoriam video. Get in your solemn mood because you know, we're about to pay tribute to some of the folks that we've lost this past year.
Yeah, you know, there's a lot of us that thought that there's just too much emphasis on the movie special effects. I mean, you hold your conference in LA, what are you going to get? But suddenly, you know, now it's interactive. Those things that were so difficult to do in the movies or CGI. I mean, I have a gaming laptop computer that I do Formula One racing on it and sports car racing and all that kind of stuff. It's better than being there.
Yes, inverse kinematic, today it's not the main element that make our software different, but in 1991, when we released this feature in the product, it was the first time that you were able to use a computer software to do complex articulated motion of animals or human body. There was no other technology to do that. Basically what we do is that we add some kind of intelligence to each of the joints that are part of an animated body. In fact, the film Jurassic Park they were able to do it because of this technology that we were the only one to have at that point in time.
The small box you see taped to Louise is a biomedical telemetry transmitter. It is monitoring her heartbeat and sending the signal to the video equipment. The red heart shape is being generated electronically by the video synthesizer and is modulated by Louise's heartbeats. The purpose of the piece is to explore the control of video images by the use of physiological signals. The outcome of the experiment speaks for itself.
getting that Oscar?
Well, that Oscar got the attention of Sony and Columbia TriStar,
Right.
and that got me to run, be the senior vice president of creative and technical affairs at Sony, and be the creative head of ImageWorks at that time. And I was fairly well known for the work I'd done at Robert Abel, which I'd had 5 Clio awards for that, and a Hugo and a Mobius award.
Wow.
Well, I always love making shots with artists. So I like working with the crew.
I see.
I enjoy when they come to show me their shot. I enjoy talking to them about what's going to make it better, what's wrong, what's great, and how we're going to solve this.
The CTO of a product that we're building called Omniverse, which is kind of the gathering place for all of NVIDIA's technology. We bring ray tracing and physics and simulation of various kinds and content creation and large language models and all of those things into a common, what we call the industrial metaverse.
This is a pen and ink, pen plotted drawing. It took many hours to execute. The original is in the Victoria and Albert Museum in London. I would suggest that this work represents the consequence of the algorithmic revolution. This example you're looking at here is a robotic brushstroke. This one dates from 1989. And it is from a frontispiece for my series honoring George Boole. This is one of 100 frontispieces, and the brush strokes for each one were made by the same parent code. And it was intended to make the point that code, that is the generator, has all the information necessary for generating the form. As is the case if you plant an acorn, and the acorn has all the information necessary for growing the tree. Okay, thank you.
Hi, everybody. I'm Ken Versprill. I'm an executive consultant at SimData. Well, model-based definition started off heavily used in the auto and aerospace industries, but recently in the last 2 years, we're seeing it really starting to have effect in many, many other industries. It is basically the ability to annotate the 3D model itself with semantically understandable information so that software downstream can actually act on the model without human intervention because it knows what it is.
Last year, the in memoriam video, I had to pay tribute to a friend of mine, Maureen Nappy, who passed away. This year, it hit even closer to home because one of our own, a member of our Pioneers Steering Committee, Bob Ellis, passed this year. So rest easy, Bob. Okay. The next thing that I'm going to be able to do, I have been, I think this is kind of the reason I am Pioneers Chair. I'm so excited to be able to share this next thing with you because we have some extraordinary guests here. Most people coming to SIGGRAPH think about digital whenever you talk about computer animation. But there was a period of time in the late 60s and 70s where there was a thriving industry in the analog world of computer animation. And it was brought about through the perseverance and personality of a man named Lee Harrison III, who lived in Denver. And so many people that worked with Lee are here with us today. I want to show a little video, and then I'm going to introduce them and have them stand for a round of applause. But before I do, let's let you guys know what analog computer graphics was like back then. Could we dim the lights?
Hello, folks. I'm Mr. Computer Image for ABC. I'm generated by a computer. My mouth is made to move by my voice. The rest of me moves because some guy in a harness moves.
Eggs.
Cub. Cube. How'd you like to be a plate? An Amoco China foam disposable plate. You'd have to be break-proof, sog-proof, sag-proof.
There used to be a time not so long ago when me and the boys could put the screws to a guy who owed us money. We'd push him around a little. You know, nothing serious, of course. Scared a wife a little too, maybe.
I'll get it.
How did that happen?
All right, which one of you's been practicing a new trick and not telling anyone?
What's the matter?
This is your last warning.
Leave at once. I don't believe it.
Hello there. I'm the Honeywell Owl. You know Honeywell, the other computer company. Incidentally, I was animated on a computer.
A character with a computer.
Lee was one of my dear friends working for Computer Image. Was amazed by the technology, which in about 1975 was a remarkable space age sort of thing.
Well, my work at Computer Image was mostly design of analog circuits and some digital, and also the cathode ray tube part of the system.
You and Lee met at Philco.
Yeah, we were both working at Philco.
He was supposed to sign off any interest in things that he was doing. He was supposed to turn it over to Philco.
Oh, yeah.
And he didn't want to do
To
that.
do that, his ideas, because, Fokker was a patent and had owned the patent.
Yeah, that was it. You and Ed.
Yeah, Ed was probably the chief.
Ed Teichman.
And I knew Lee, I met him at Denver Research Institute at the University of Denver, probably February of '68. One of the salesmen, Bill, I can't think of his last name, said, well, if you can animate the alphabet, we'd have lots of sales and so forth. So we used Animac as a test bed to show that you could create a raster and then use a camera to display on that raster and move that raster around. I remember Francis Honey, who was the chief engineer, told me I got 1 or 2 months and $5,000 to build a system that used a camera and rasters to produce animation. We worked real hard, Joe Santastaven and myself, to build this prototype Scanimate. We got it done in January probably of '68. Then we started publicizing it, like that's when Tommy Smothers came on board member or something. I was engineering, but I also did the animation because nobody knew how to use the equipment to create animation. I was the initial operator on all of the systems that we had there. Animac and Scanimate and Caesar, later on the System 4. A couple of first operators used to be cab drivers, Jack Wilmore and Red Daniels. But like Red Daniels, we got to know people very well, I guess, from being a cab driver.
I'm Donna Santastaven, and this is my husband, Joe.
I was a electronic technician, computer image. I worked with a whole bunch of engineers at the University of Denver, and they designed circuitry for the Air Force. Lee Harrison was starting up a company. They wanted me to work for nothing, for free, but that wasn't going to work because...
Well, at the time, I happened to be 8 months pregnant. Just quit my job. You were already working for them free in our basement. It was either a ping pong table or a pool table. We can't quite remember. And he would work nights and weekends. I told Joe he can't go to work for Computer Image unless he gets a paycheck. So you became the first paid employee.
Yes, that was in
1968. And Joe saved the letter, $630 a month with fringe benefits. I have no idea what the fringe benefits were, but it was a job, and we could live on that at the time.
Well, now that might actually turn out to be that you were the first person ever hired to make money doing computer graphics.
Oh my goodness, that would be nice.
Well, he was always a man with a dream. He was following a star. He told me about it. He was working for Philco Corporation in their research department. His dream was to do animation by computer, yes. He thought in terms of a mechanical kind of, I guess it wouldn't have been a computer, would it? But a mechanical device to do animation. So he became a mechanical engineer. Later on, he thought that was a mistake. He should have been an electrical engineer. He spent a day or two at the movies seeing Fantasia over and over again. He had Lee Harrison Associates. They needed parts, so they each paid $5. People were not paid. Nobody had any money. The first machine they started building was called Animac. It was done with tubes and wires. It started in an attic. The men would come over of an evening. This was when they were paying $5 a month. He was always talking to a lawyer, either about a patent or about a corporation or whatever it was. So he was not a businessman. He had to learn that part. We moved to California in '70. The office, the computer image office, was in the Smothers Brothers building because Tommy Smothers was on the board. When there were board meetings, they would come to Camarillo, and Tommy Smothers would stay with us because he was too recognizable to stay in a motel.
We might not be aware of it, but we're all watching more computer-generated television these days. Lee Harrison III of Denver was and still is a pioneer in the development of computers that can create animation. Channel 9's Mike Landis has a report on the animated computer.
This was the beginning of the Computer Image Corporation, and it was a rather unlikely one at that. The employees didn't get a paycheck. In fact, they contributed $5 each month to buy parts. The animation itself was simple, even crude.
And you notice we have many inputs here, and
Lee Harrison moved to Denver in 1965 and built his second computer, Animac, 2 years later. It was far more sophisticated than the first, and it utilized a unique electrical harness worn on the body and attached to the computer. When the person wearing the harness moved, the animated character moved. Characters that could be produced with Animac were far too abstract for an audience accustomed to Mickey Mouse. But clients did like the special graphic effects. So in 1968, Lee and his associates built Scanimate. In 1972, Lee won a national Emmy for the development of Scanimate. He says it's difficult to watch television without seeing something produced on one of the world's 8 Scanimate machines.
People would certainly recognize probably the Pepto-Bismol commercial.
Whoever you are, whatever you do, wherever you go, sooner or later, you're going to get indigestion. That'll be the time for Pepto-Bismol.
Indigestion.
Pepto-Bismol.
Indigestion.
Pepto-Bismol. It coats, soothes, relieves.
Go ahead and lay that down. Right. All right.
But Lee still wanted a computer that could duplicate the movement of a cartoon character. And Scanimate, although good enough to win an Emmy, just wasn't it. So in 1969, Lee and his team of video engineers designed Caesar. And according to Lee, animating with an electrical harness became a thing of the past. Today, Scanimate and Caesar are often electronically tied together to create animation. Animator Dave Holman sets up 2 keyframes, punches a button, and the computer does all the tedious work in between. And the future? A new computer animation machine called System 4 that combines the best of Scanimate and Caesar and does even more. It'll be ready for use this summer. But for all this wondrous equipment and new technology, Lee claims we've only just begun to understand the potential of computer animation.
You try to imagine what the world would be like if all of a sudden today, all of us for the first time were given vocal cords to speak with so that we could communicate this way. Well, I think we're in the process of being given some servant of the visual imagination that will allow us to communicate in a very marvelous and exciting way.
It gives me an extraordinary amount of pleasure, thank you, to introduce some of the most amazing pioneers in the history of computer animation who are here with us tonight. Mary Lou Harrison, her children Paul and Rabbit Harrison, their grandson Sam, Joe and Donna Santastaven, Gary Teichman. Please rise and give these guys a round of applause. Okay. Oh, and I wanted to show you guys this. We can bring the house lights back up. I still have this. This is a cardboard model of the Scanimate that came from Computer Image. It's been on my desk for years. So this is what the Scanimate looked like, a little bit bigger than this though. So thank you, you wonderful, wonderful people. I'm so glad you were able to join us here tonight. Okay. Now it's time for our featured speakers. So Mary Whitton and Nick England are going to come up, and it's going to take a couple of seconds to get their presentations on the computer. And they asked me not to introduce them because that's part of their intro, so we'll let them introduce themselves. So let me get your presentation.
Well, we're not going to talk about basketball or barbecue, but we will talk a little bit about pixels and building programmable processors. What's the best way to introduce this? Well, I guess let's set the Wayback Machine to 1972. I had a little bit more hair back then. 1972 was a long time ago. That's a half a century. A half a century before that, the first radio broadcast was made. So we've probably come a little ways since then, but we'll see what happens. In '72, I showed up at John Starhammer's research lab at NC State. John had started the lab in between when I was an undergraduate and did some work for him, and he started the lab to do computer graphics around 1970. I showed back up in '72 to learn something about computers, and I walked into his lab, and there was a 3D vector display, part of an Adage AGT30 computer, and they had just gotten running a color display on the side, a full color display. And I was just blown away. I thought this was probably the greatest thing I had ever seen in my life, and it certainly, except for Mary. Mary was the best thing that ever happened. We're married, by the way. John had accumulated all this hardware, so there's a computer. It was really great at doing graphics. It had a lot of good features. It was a 3D display with a computer built around it, and that didn't happen for many years later, 10, 12 years later, before anybody else had one. I mean, it was huge, but in terms of being able to use it and use it for graphics, it was wonderful. It had indirect addressing, you know about indefinite indirect addressing? That's when you look for some data, but what you really get is the address. That is, the memory system says, these aren't the bits you're looking for. Go look at those bits over there. Well, those address that you then use to go find some more data might tell you, oh, we're not the data you're looking for either. Go look over there. You could get into a complete loop. Sitting right next to the monitor there and the keyboard was a big button that would stop everything right there because you'd just gotten off in the ozone. John had also accumulated one other thing, which was a Varian mini computer. And the folks that were in the lab before I got there had attached these two things together. So it was a 16-bit mini computer, and it was attached to a color display. You can see over there on the, you gave me a pointer one time, but I don't know what happened to it. Anyway, you can see over on the right-hand side what looks like a color TV. It's just a Sony color TV, but it had a video disc hooked up to it, and you could write scan lines from this Varian mini computer off to the video disc. And one of the things that I did when I first got there was to build up an interface to a RAN tablet so you could draw things. And I made a little sketch program, and then Debbie Ogden, who was the only person with a computer science degree in our lab ever, I guess, she got an undergraduate degree in computer science, but she wanted to learn something about hardware, so she joined our lab in the EE department. She wrote a really nifty textile paint program, and she wrote it all in assembly code using a paper tape system for doing compilation, et cetera. It was pretty crude, but it really worked great. We had fun, and we had fun with stuff that other people didn't get for a decade or more later. And that's one of the things that I think is great about universities that can build stuff. It may be big, it may be ugly, it may not be as fast as you want, it may not be commercially successful, but it gives people the chance to experiment with things and to do research that they couldn't do otherwise. It's tools for research, all right? And as we go along, I'll tell you how we didn't make any money building those tools. If this works, so this is Jeff Eastman. He and Debbie wrote this little modeling program that ran on the 3D vector CRT. And then Jeff's scan conversion program would run on an attached graphics processor. This happened to be that Varian mini computer. He did sort of a Watkins algorithm, but that's about how long it took in order to do something. Here's my one and only animation. All right, it was done on a Super 8 that I went click, 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 and that was it. All right, good, we made it through that. Well, we messed around in the lab and had a great time doing it. In 1974, the first SIGGRAPH had 4 papers from our lab, which was more than UNC, Cornell, MIT, Utah combined, all right? But they let any sort of paper get in at that point, I guess. Anyway, in 1976, NASA came in the lab. I think they also had an AGT, and they said, we really want to do display of these kinds of cockpit displays that we're now doing on vector machines. We want to do them on raster machines because we're going to put raster displays in aircraft, all right? And the way they were doing it at that point was point a TV camera at a vector display system and then use the TV signal in order to put the display in the aircraft. But they wanted to do it straightforward, straight to raster displays. The one on the left was a sort of the thing, that's the kind of thing they wanted, and eventually they got, and eventually turned into the displays that you see in aircraft all the time. Every time Mary and I get on a plane, we appear in the cockpit and say, yeah, we know where that came from. All right, it went from mechanical instruments to LCD, well, originally CRT, and then LCD panels that carried all the instrumentation. On the right is the first thing that I built, which was a device for drawing vectors on a raster system. So it had a frame buffer, it had a processor, it would draw vectors, and it would do it in real time. It was fast enough to do it in real time. I'm not sure there were any that were doing it at that point. And I said, drawing lines is okay, but you really need to do a lot more stuff than lines, particularly when this guy Turner Whitted, he's looking at some control points for a B-spline surface. This guy Turner Whitted showed up, and he started doing translucent curved surface shaded stuff, and I thought this was really cool, but how could you make a graphics processor that could make things like that rather than just draw lines? So I built this gadget that was a programmable graphics processor, because I didn't know what I wanted to do with it, but I figured other people could figure out something to do with it, and I might figure out some things to do with it, but at least it satisfied NASA. They were happy. Actually, the follow-ons to this ended up in pretty much every NASA lab and every aerospace company's lab. And it used a new chip that came out. It was a 4-bit part of a computer. So this was a 32-bit computer. I know you needed to do 32 bits. You couldn't get away with fewer than that for the kind of stuff I wanted to do. It had a 64-bit wide instruction, so it did a lot of things at once. The whole idea was you could do you increment a loop counter, you test a condition code, you add some numbers, you do some more stuff, you write some data, you read some data, and all that happens in not just one instruction, but one cycle, all right? So very long instruction word, you try to do a lot of stuff at once. This idea had been used in computers as writing microcode to execute bigger instructions, but typically you'd use, 10 instructions in order to do an add of 2 numbers, say. What I thought an instruction ought to be was draw a patch, trace array. Well, that came later. But do something big, all right? Not just make an add, but write code that would do a lot of stuff. And that's what we did. It also was the time when new memory chips came out. You could bit on one board 256 squared by 8. This was amazing. All right, it used to take lots and lots more boards, but at this point you could do some pretty good stuff. I had a paper in SIGGRAPH 78. Turner and Mary and I all went to SIGGRAPH 77, got completely wowed, and came back and said, we need to do a lot of stuff. And so we tried. This was an augmented reality system that I did for trying to create models of curved surfaces. This is 2 TV cameras looking at a little toy car, and I was interactively fitting a B-spline surface over the car by manipulating control points. So it was a merge of the TV camera video and the video from my graphics generator and the little program that I wrote to do that. So it was a pretty early AR system of a sort. It didn't work very well, but it was a lot of fun to play with. Well, Mary and I, we had people come through the lab and they saw that. NASA said, this is pretty cool, we'd like to get one of these. Lockheed said, this is pretty cool, we'd like to get one of these. Chuck Surrey at Ohio State said, this is pretty cool. A bunch of people came through the lab and said, we'd like to get one of these. So Mary and I decided that we would start a company. All right, neither one of us had any experience at all with starting a company. We did it in the back room of our house, and the first purchase was an electric screwdriver in order to disassemble my model railroad. We turned the model railroad room into our, quote, R&D lab. This was the back room of our rental houses as grad students. That's Mary working on some code. There's an LSI-11 in the back. It's actually a Heathkit LSI-11. Mary built the Heathkit for this machine. That's what we did all original development on. I built the ADM3 CRT terminal because that was a kit too. All right, and eventually people kept wanting to buy these things. And so our original business plan went out the window. The business plan was, we knew there were maybe 4 people that would want one of these things to play with. We'd build those 4. We'd take whatever money we got. We'd go to Europe on vacation. And when the money ran out, we'd come back and get real jobs, okay? It was 6 years later that we made it to Europe, yeah. And probably 150 systems later. I don't know what it was, but like many of our plans, it didn't quite work out. We started off by bringing in part-time students who would come in and they would do quote manufacturing of these systems. So we eventually graduated into regular-looking systems, not quite so handcrafted, but the early days were handcrafted. The first system went to a friend of Henry's in Dallas, Texas. I'll tell you a little bit more about that in a second. Second one went to Turner Whitted, our buddy who had graduated and gone on to Bell Labs and was doing stuff with Rays or something, I don't know. And Henry and Fred Brooks bet on us for the third one, and it sort of just snowballed from there. I'll tell you why Henry's acquisition was really important to us. Our motto is we strive to meet the requirements of advanced research groups, which meant that if somebody said, could you do this? We'd say, if I had the faintest clue about how I could design that, I'd say, oh, sure, yeah, that would be a crossbar selector. Henry says we want to take any bit out of the frame buffer and we want to run it into any bit into the lookup tables. I said, yeah, I think we can probably do that. I think Mary designed a crossbar selector. I don't know. Anyway, so we had a 32-bit processor. Mary designed a matrix multiplier unit that was separately, it was a coprocessor. It was separately programmed. It mostly was used for doing matrix multiplications and perspective division, but she also programmed it to do surface patch evaluations. And you could program it to do whatever you wanted to. They all worked on a bus. We made this, it looked better after a while. It didn't quite look like the one from the lab. This is Mary's matrix multiplier, all right? And eventually we made a system. We still used our Heathkit LSI-11 computer to do demos at trade shows because people would say, holy crap, if you can do that with a Heathkit, what can we do when we hook it up to a VAX? But really, all the power was inside the graphics box, the graphics engine that you could program that was directly connected to the frame buffer, all right? We made an open system. We made it for researchers, and that was, we gave you the schematics. Turner decided he didn't like something, he rewired it. We gave people bare boards, specs on how to do it. We built a whole bunch of weird stuff. Anybody would say, somebody said, so if you've got this thing called, you got 32-bit pixels, right? So red, green, blue, and then there's another 8 bits. Suppose we use that to blend between 2 images. I said, okay, we'll build you a real-time alpha blender. So 2 frame buffers in the system and a blender that would multiply by alpha and 1 minus alpha and add them out to go out on the outside. Customers also built hardware. People built, well, there's a list down there. Lots of weird stuff. Henry and his group at UNC built a number of weird things. But the best part, of course, was it was all programmable. It was user programmable. People had built processors that were sort of like this for graphics machines, but only the engineers at the company that sold you the thing could program it. We gave people source code, an assembler. We gave them source code to libraries that we developed. We did stuff for, your traditional ZBuffer polygons and texture maps and bump maps and things like CSG and ray tracing, and a lot of stuff for doing volume rendering, for example. We gave all that code to people, and they did stuff with it. But they wrote tons of their own code, and the reason they could do that was because one of Henry's students, Gary Bishop, wrote a C compiler for this thing, because writing assembly code for this 64-bit wide instructions was a real pain in the butt. I mean, it was horrible looking code. It really was. Some people did it. Doug Kay and George Joblove did some, and they managed to survive. Good guys. They worked on number 1 down in Texas, and I'll show you a little bit what they did. Also, Preston Gerd at University of Waterloo, which was another one of our wonderful customers, wrote another C compiler, and so they used that to do a lot of weird stuff at Waterloo. People just did lots of great things, and that was so good for us. We did, not like we said, we originally built it for research labs. 90% of our customers did research work. We sold a few of them to people that built systems that they then made multiple copies of. Some real-time graphics, you can read that. And then we get these, we'd see people at trade shows, and they'd come up, and their badges were different from the last time we saw them at a trade show. Not their company, but their names were different from every time we see them at a trade show. It used to be John Smith, and then it would be Fred Chapman, and then it's the same guy. What's going on? And then we get an order from the Maryland Procurement Office. Okay? And they always paid on time. We always shipped to some address in Maryland, and we're not quite sure where they ended up or what they did with them. They always paid on time. They were good customers, yep. So we sold a bunch of systems to the aerospace companies. They used them to do their cockpit instrumentation simulation. Some of these systems were still in use in 2000. All right. This was a system designed in 1979, and that's scary to me that people were still trying to use them, but they were used in simulators for training. The one on the right was from our very first customer. They used the video capture to get slice data from microscopes, and then they did reconstruction of polygonal surfaces for anatomical structures. The ZBuffer and shading code was written by Doug Kay and George Joblove, and it's amazing that they not only survived, but they later bought the first system that went to the CGI industry when they were at Marks & Marks. So it didn't scare them off too much. Let's see, if I get lucky, this will run a little program. Well, just one of the things that we did for somebody. This was for Alcoa. They wanted to know how beer cans crush. Well, it's important if you're going to stack a Z in beer cans, you'd like to know what they're doing. But we added some stuff to do. This was real-time decoding. So we rendered a bunch of images, but then it would animate things. That was good. We had one customer that used, I think, 7 of these things scattered around on a ship. This was a ship training system. So each window was an Icona system. We liked those customers. They were good. Henry's group at UNC did something that I thought was really clever. They did a lot of molecular modeling kind of stuff. But one of the things they did was use the TV camera to look out into the room where somebody would hold a flashlight, and then they would do deferred shading, I guess it is, because they would change the color maps in order to change the highlights on the molecule. Okay, that says I'm going to run out of time, but we'll get there real quick. All right. You'd move the flashlight, and the shading would change on the molecule. I don't have a video of that, unfortunately. I want to show you this one. This is going to run. I'll get through this. We did, Tim Van Hook came from Ohio State, and he did bump mapping and reflection mapping and regular texture mapping and things like that on B-spline surfaces. So it did adaptive subdivision of curved surfaces. He also did a tool that did CSG. This is a real-time demo. So this is subtracting this little milling thing from a solid block of something. All right. I'm going to try to get through this. All right. And Tim eventually used it to do ray tracing. It was a really nifty, he had a paper in SIGGRAPH 86, I guess it was. But this was entirely ray traced in 1985 inside this graphics processor, this programmable graphics processor. It wasn't real time, but it was pretty fast. I'm just going to keep on talking, Ed. Are they going to toss us out?
I don't know if they're going to toss us out or not.
Okay, Mary, you yank my arm if you want me to quit. Okay, okay, all right. You'll have to come back next year for Mary. We did a second iteration. Tim Van Hook and Mary and I started a little company called Transept Systems, and this time the world was changing from a fax with a big box hooked up to it to a workstation with a couple of boards plugged into it. We did the couple of boards, and we did a lot more processing on it. This was a nifty thing that we did was to integrate it not only into the hardware by plugging in boards, but into the software. We created a chroma key, you know, a green screen kind of thing. If you created the correct color on a circle, I mean on a square, or you know whatever size you want, in the Sun window system, it would switch video and come video from our board, all right, instead of their board. So this window of a ray trace thing is coming from the graphics processor, our graphics processor, and the rest of it's coming from the Sun video. And Bill Joy from Sun comes up to look at the demo. He plays with it for a little while. He said, "You did a really great job on putting the window system onto your hardware. It's even got the same bug on overlapping windows that we do." But we just finessed that. We put a lot more processors together on this board. Two 32-bit integer processors, a floating point processor, an integer multiplier accumulator, barrel shifter, lookup tables, a whole bunch of stuff. All right, and it got to be a 200-bit wide instruction word. I don't think anyone ever wrote 200-bit wide. No, I take it back. We did because we had to optimize some stuff. But that was a real bear. But we started off with the C compiler to get started. Okay, we're going to do this just briefly. So you remember that demo I showed you earlier of in the NC State lab of rotating something around and then it was scan converted? This isn't a slow loader. This is a fast ray tracer, all right? This was 1986. This was a pretty fast ray tracer. It's an anti-alias cone tracer. We were doing a demo, and this guy walks up and says, "I see these are anti-aliased images. How are you doing that?" I said, "Oh, there was a paper a couple of years ago in SIGGRAPH about doing cone tracing, and it gives you anti-aliasing. It's by a guy named John. It's the same name on your badge, isn't it?" It was John Amanatides. That's right. Okay. So we did a lot of visualization kind of stuff, raycasting through volumes, some more high-quality rendering things, a RenderMan library that worked on it. And the last project that we did, we got bought by Sun Microsystems, so we could hire some more people. We hired a bunch of people from Henry's lab. That was great fun. But the last thing that we did at Sun was to make a thing that used multiple processors. Each one of these circles there on the right-hand side are heat sinks for an Intel i860, which is a VLIW kind of processor. And we used video RAM that would stream video in and out, not to stream video, but to stream data between processors. Unfortunately, Sun pulled the plug about this time, and so these really never got used very much. But the few things that we did on it worked really cool. It's really great. We also finessed the Sun operating system, Windows system, once again. There are two chips on the left-hand side, upper left-hand corner. That's the prototype NVIDIA chips. When Curtis Preem and Chris Malachowski were at Sun, they did this chipset called Lego. GX was the product name. One of them does transformations, the other does drawing in 8 bits. But that's the prototype. That handled all the Windows system stuff, and we just did the weird volume visualization and things like that in our system. Sometimes you get a little too early. When Sun closed down our group, one of the groups did some video processing boards for Sun, video capture. They started a company called Osprey. They became the standard for capturing streaming video. They really just sort of took over the industry, and they had this idea. How about we put your video on the web, yourvideoontheweb.com, 5 years before YouTube. You look at the list of what you're going to do with it, weddings, graduations, soccer games. If only they'd put cats in that list. You really want me to keep talking, or shall I stop here? Okay, we'll do that, all right? All right, so what I'm going to do is elide over what I was going to talk about, what happened down the road. Down the road, 24 miles away, was Henry and his lab at UNC. And they did a series of amazing machines. They were SIMD instead of being very long instruction words. So we did one processor that had a bunch of functional units. They did a zillion processors, millions of processors. But I'm going to elide that and turn it over to Mary, and she's going to talk about what she did after Sun sort of 25 years ago kind of went, okay, you're all done. All right? I have no idea how to quit.
Please.
So Nick has talked about the computational end of systems, and I'm kind of taking an even bigger systems view because I'm looking at the systems that it takes to do VR. And so he did the dark orange part of it. And in the whole loop, you've got a user, pesky people, humans, they're very complicated. Input controllers, technologies, devices, head trackers, and handheld controllers. The computing part that displays the head mounts and headphones, and then back around to the user. So I'm going to talk about trackers and controllers and trackers and head mounts, essentially. The first tracker, Gary Bishop, you heard his name with the C compiler, built what we refer to as the antlers, had a light on the end of each of those 4 spikes. The Iconis video input would look at it and figure out where that thing was. To use it, you had a little television that you held underneath the tracker, held it up to your eye, and looked at the image that was taken by camera that was in front of a vector general, stroker. So it's over there, you can move your head and see it. Single, not stereo at that point. We made a lot with that. This is all before my time. A lot of very strange head mounts. And they're early. Think about '86. There weren't very many commercial. You had to roll your own. This one was another one that had 2 cameras that looked at the front of an ENS system and came to 2 TV screens that were in the top of that device. The next one was called Snail Eyes for obvious reasons. It was custom, it was color sequential, was something weird about that one. Another one, this one had big LEDs, it was a bicycle helmet, and the TV cameras for it are on the back of it, and actually was used for a lot of demos. In SIGGRAPH 91, UNC went and showed the system off. There was a treadmill that you walked on so you could move, bicycle handles to steer yourself, and then you saw architectural view of the then-to-be-built computer building at Carolina. So then we built, I got there in the middle of this, 3 generations of inside-looking out trackers. The Antlers had the video camera looking in at the 4 lights, and the new tracker, which ended up being the Highball, had a sensor on your head and looked up at the lights in the ceiling. There were a lot of them. The lights flashed one at a time, and so you always knew where they were. The lights were embedded in panels that fit into drop ceiling tiles. The very first one had to be laser aligned so that you really could know where the position of each of those lights was. Then the next one was this tan panel, and somebody had done a auto calibration by that point, so you could do it by yourself, and the little strips in the front were when the tracker became commercial. So we used it. Oops, wrong direction. So you've got these lights up in the ceiling, and you've got this head mount, VPL head mount, and how do you look at them? Well, at that point, you put 5 cameras and hung them around your head. Obviously, why it was called the chandelier, and the back view of that. The next generation, again, another homebrew head mount that was very good at precision because of the application it was going to be used for, but there was a cluster of cameras on the back. So that gave it, so it was a little easier. And then that evolved into the Highball, and I took out the picture that had the hand. It's about that big. You can hold it in your hand nice and easily. 6 sensors are behind the lenses that you see there. They're lateral effect photodiodes that plug into the board there, and that's how those 6 look up at the ceiling. The lights blink one at a time, and it figures out where it is. Very accurately, 2,000 times a second. It was the first tracker that I ever was in a head mount, and you looked out, and the world was completely steady. You guys who've used magnetic trackers, remember how the world just went like this? Yeah. Okay. There's the commercial Highball on the back of an Invis. That was our workhorse for a long time. The last thing we built was an AR video see-through for medical applications. The optics were folded, so the cameras were aligned with your eyes. The previous ones we had done for the video see-through had been offset from the eyes, so the physicians had trouble with the alignment. And it also flipped up, so when the doctor got to the point and said, "I can't do this with this," and took it off, it was easy for him. And this is one of the applications that Henry's team did doing breast biopsy. We were working with the Phantom. I think that system had 4 different tracking systems in it. It was pretty amazing. Molecular modeling was a big deal at Carolina. It goes back, so we're going back in time a little bit. There were just a lot of belief that molecular modelers could use the power and the information that could be gotten from computers. Notice that this visiting scientist who was at Carolina working on the system, look how many knobs and dials and sliders and things there are. There was something like 19 parameters that you could set directly from the interactive devices. Stereo is important. That's pointing at the lorgnette made by Evans and Sutherland. It spun around and went left eye, right eye. It was coordinated with the display. The Bausch & Lomb also made something. Here's what it actually looks like. We always called it the spinning orange juice can. Had holes in it so you could alternatingly see out of your one eye or the other. These are 4 different renderings of a molecule, and one of the claims to fame of this project at Carolina was that the first molecular structure that was done without building a metal ball and stick model was done in the lab on this system. And there's some dispute as exactly what it was, but we're pretty sure it was this SOD molecule. That's what the lab looked like. There is circled up there is they wanted to do drug docking and fit the drug molecule into the other molecule and to feel the molecular dynamics. So force feedback and haptics was important. So they went to Argonne and got a remote manipulator that had been retired from dealing with radioactive materials. We got the non-radioactive end of it. The new building got built, and the arm was moved over there, and that is in place there. But you can see now we have gone from having vector to doing raster and solid shaded on the molecules. Now, how this whole project changed when we began thinking about, well, some people came and wanted to deal with an atomic force microscope, which typically scans across a surface like that. And the smart people said, what if we could control that tip ourselves, and then we could poke on things? So they made a nanomanipulator. It, again, depended upon having force feedback and haptics. So this has 3 generations of the haptic feedback. And it's really kind of cool because there are pictures that you could push gold atoms around. So it's quite neat. So all of those things are, we rolled our own really weird things, and then many of them became commercial interfaces. About that time, Dr. Brooks went on a sabbatical to the UK, and while he was there, he visited Mel Slater's lab at the University College London, where he first saw the demo of the pit, looking down into that. So the UCL pit was a long room that you walked around in, then you go and you turned and you went into a room where the pit was. This was the Carolina version of that. The fellow who had done it, worked on it at UCL, came and spent a summer with us. They had tested the difference between people who moved around, who did locomotion through the virtual environment with a joystick and a controller, versus people who did it with a walking in place technique that was based on a neural network. But I have to tell the story. The guy who did it, Martin Uso, had this very peculiar gait, and that he had trained the neural network. I could never make it move. So that's sort of what it looks like when you get scary. And let me see if I can make it go. All right, so this is walking into the room, looking off the end of the diving board, and the top, that is heart rate and skin conductance. We began studying response to this scary thing, the stress responses, the physiological responses to that. Now we're going to see a young lady who is going out there for the first time here in just a minute. And one of the things we do is do behavioral observations and watch how people react to this. And I'll talk about the boards in just a minute. She's very hesitant. Yeah. So we did this study, and we had optimized everything, and we found out that people really did get scared. And Fred said, "It's wonderful, we can make great virtual environments. We've optimized all these things and it's perfect." And I said, "Fred, we don't have a clue which one of the things we optimized really matters." And I actually went back and asked him if I really did say that to him, and he said, "Yeah, you really did." So, but that got us started on an entire thread of research, which was looking at each of the factors individually and varying them in terms of quality and seeing what the response was for people. And that led to our team being named Effective Virtual Environments. What does it take to make it effective? So there was parallel work going on in passive haptics. If we have you walk along the ledge and feel it, will that make it scarier? The styrofoam blocks over there were to hold on to because it did make it scary. Things were kind of a mess because it took a lot of cables. There are 2 cables to the hand tracker. There's the physio cables and there's the head tracker. And what we had people do was to walk out to the end of the diving board, and they would either have the boards or not, and curl their toes over. It was about 2.5 inches, and you could tip your toe and not hit the ground. So that was good. So we were trying to say what we'd been evaluating with just questionnaires. And questionnaires really are pretty not great measures. So what makes a good measure? It needs to be objective, sensitive, valid, reliable, contemporaneous, happen at the same time. So we began looking at the physiological measures to see if they would correlate with the presence measures from the questionnaires. Skin temperature turns out it's too slow. We need fast reacting things. Skin conductance, the little probes didn't stay on our fingers very well, so that didn't work very well. Regular, just heart rate, there's too much population variability, but change in heart rate turned out to be a very good metric for us. And we did the studies to do the validity, the reliability, and sensitivity measures. Okay, so we were walking out there, and then, oh, you know, we're stuck. We can't get any bigger than our tracker, than our space. Let's see what we can do to make it.
A blindfolded subject, when instructed to walk in a straight line, may actually walk in an arc. Humans rely on visual, vestibular, and auditory cues to orient themselves. We are exploring what happens if a virtual environment user is presented with a virtual scene.
Okay, so could we rotate the scene slowly around you and get you to walk this way instead of walking that way, because you may be in the lab and you're going to walk into the wall. So the first order question is, can you make it work at all? And then you worry about whether is there some effect that will affect performance or your cognitive abilities. So this is a little video of a woman. She's walking along a white line that's on the floor in the lab, and the inset video is the virtual scene. Oops, sorry. The virtual scene that she's seeing.
We show a subject walking back and forth along a straight line in the virtual environment. In actuality, they are rotating in the lab, and the result is that the user walks in a star pattern.
Okay. So Sharif made this environment. Sharif Razak did this work originally. Environment on the left, you came in and followed the path that is on the right-hand image. Now, this is really cool. This shows you the path in the virtual world, and in the red part is the lab, the tracked area in the lab. So they were going back and forth in the lab, and we're going then in the zigzag pattern in the So the trick is, and it turns out that it's really true, that if you're moving your head already, you can insert a lot more rotation than if your head is just being still. So how can you get that, force people to rotate? Well, you can design the environment so they have to, but that's very limiting. So a woman named Tabitha Peck said, well, what if I have something that I can add to the environment and that you follow and look at it with your head, and then then we can insert a lot of rotation and get you away from the walls. So the distractors appear if you're too close, or we can put them in there to preemptively move you. But then the question, again, is does it upset or degrade your cognitive functions? Okay, Tabitha made this environment. People started down here in the lower left, and they moved. We're going to see, I'll try to speed this up. You're going to see the, come on, mouse. Well, I'm not going to let that run. You can see that these are to scale the virtual path area and the real path area that was the lab. And what that all ends up looking like when you get to the end of it is they look like that. That they have gone the paths in the left-hand big image, and in the real world they have done that. So then she said, okay, go back to the beginning and point to where each of those colored things were. Well, they kind of did okay, and they kind of didn't do okay. And I have a slide that says, put some more stuff from Tabitha in here, and I forgot to do it. Okay. So some of the things we studied, and it's one at a time: locomotion, frame update rate, latency. This was back when we were doing latency at 50 and 90 milliseconds. Things have advanced since we've done that. The passive haptics, those boards. The rendering quality, did it matter? Field of view, spatial audio. And we did this with different kinds of measures: the questionnaires, physiological measures, performance measures, psychology, psychophysics, and ethnographic observations. We really learned that the more kinds of measures you can use, the better, because they all have high points and weak points. So the triangulation, and if you can get them to all point to the same answer, you think that gives you more confidence in the result you've got. The greatest compliment we got on this work was Dr. Brooks gave a lecture in the Heidelberg series, and he got done, and Ivan Sutherland walked up to him and said, "I had no idea you'd done so much science." And we kind of thought, oh, this is good. And our greatest product, as Dr. Brooks would always say, was our students. So, thank you very much.
Okay, well, thank you guys for coming. This was great, and thank you for Mary and Nick. Let's give them another round of applause. And thank you again for the wonderful, wonderful analog pioneers who attended tonight with us. So give them another round of applause. I forgot to mention there was someone else in the audience, Susan Krause, who was an animator at Computer Image back in the day, and she was one of the first women animators maybe in history. So I wanted to acknowledge her. I think she may have left, actually. But thank you guys for coming, and we'll see you next year.